Today is the dot product of algebraic vectors. So the difference between today's lesson and yesterday's lesson is that when we have geometric vectors, we're going to have their size and the angle. We're going to have this the look of the vectors. We're going to have the arrows and so on. Here we're going to have the algebraic version of it, which is just the pair of coordinates or the triple coordinates. You're going to see this extends so nicely to 3 dimensions. That's where its power really lies. Very few examples here, just a couple of quick examples. Unbelievable in their simplicity and shocking in their power. The dot product of algebraic vectors. Using our knowledge of operations on Cartesian vectors, we could derive the following property for dot product of Cartesian vectors. Doing some geometry, we could draw the two vectors. It's not part of this course, but it wouldn't take much to establish this, is that if you want to do the dot product of two algebraic vectors, that is, you want to dot product A and B in the Cartesian plane, all you do is multiply their x coordinates. So that's what this formula is saying, is to get the A1, B1, you're just multiplying their x coordinates and adding that to multiplying their y coordinates. Basically, you're multiplying how far they go in x and multiplying how far they go in y and adding that all together to find out how much they go in the same direction together. That's a very complicated sentence. I totally get it, but it's just giving you a taste of what this thing accomplishes. For now, you don't really need all that. For now, it's just about getting to know what do we do when we have an algebraic vector and we want to dot it with another algebraic vector. It's really as simple as what this example shows right here. Find the dot product of u and v, where u is 2, negative 4, and v is 3, 5. So if I want to go u dot v, and this is the same dot product as yesterday, it's just that we're calculating it with the components instead of, we could draw these things out and we could go through all the procedure of yesterday, magnitude u, magnitude v, cos theta, but we get this answer here. That's the beauty of it. You multiply the x's, so 2 times 3. You multiply the y's, negative 4 times 5. It sort of feels like distribution, but it's not. And you just add all that stuff together. Negative 14. The negative is completely weird here. And it sort of says that these two vectors operate in opposite directions to each other. One's pulling back on the other one. It's sort of like my wagon example. Instead of you pulling forward on the wagon in the direction the wagon's going, you're sort of pulling backwards on the wagon, away from the direction it's going. More about what this means later. Don't worry too much about what it means exactly yet, because that all comes as we go along through applications. For now, we just need the operations. One more example here, and it's unbelievable what we can accomplish here. Apparently, using the weapons we've got the past 2 days, 2 3-dimensional vectors. One that goes 1, negative 3, 2. Good luck picturing that in your mind. And another vector, 2, 7, negative 1. Again, very hard to visualize what these two vectors are. But we can find the angle between them, unbelievably, using this formula from last day. And like I said before, I don't memorize this thing, actually. I just rearrange from the original formula. But since I've got it here on the page, I'll just use it. Cos theta, the angle between these two vectors, is going to be u dotted with v over the magnitude of u times the magnitude of v. Now, there's a little bit of tricky work here to do, but it's not too heavy compared to the power of what we're got here. So I'm going to go over here and do some side work just so I can fill it in afterwards. The first thing I'm going to need is the numerator u dot v. And to dot algebraic vectors, I multiply the x's. So 1 times 2. And I add that together with multiplying the y's, negative 3 times 7. Add that together with multiplying the z's, 2 times negative 1. So the dot product extends to 3D, just like, see, let's extend it to 3D here. If A is the vector A1, A2, A3, and B is the vector B1, B2, B3, then A dot B is equal to A1, B1 plus A2, B2 plus A3, B3. And extends to other dimensions as well. But okay, we're only doing 3 dimensions in this course. So when I do all those together, I get 2 and negative 21. I get negative 21 for u dot v. They're sort of operating in opposite directions, just jumping ahead a little bit because I get a negative out of this. Okay, so we need magnitude of u in my equation over there. So magnitude of u is a little 3-dimensional Pythagorean theorem here. Magnitude of u is 1 squared plus negative 3 squared plus 2 squared. And I get, 9, 13, 14 there. Magnitude of v is square root. Where's v? Okay, 2 squared plus 7 squared plus negative 1 squared. And I get magnitude of v. 4 and 49 is 53, and one more is 54, which does, you could simplify that radical, but based on what I'm doing here, I don't need to simplify the radical. So back to my cos theta formula. Cos theta, u dot v, I found out was negative 21. Magnitude of u was root 14. Magnitude of v was root 54. So theta is the cos inverse of this giant mess here, which my calculator can handle no problem. I'll just type all that stuff in. And the angle between these two three-dimensional vectors is 140 degrees. Maybe you weren't surprised. If you're right with it, when we saw the negative there, we knew the angle between them had to be obtuse. If that's not perfectly clear, that's okay. Don't panic about that. I'm just trying to relate all those things together. So, dot product, the two versions of the dot product, the geometric one from yesterday and the algebraic one from today, combine to be able to find the angle between two three-dimensional vectors in fairly easy steps. Just try to fathom that for a second, that you got two vectors sticking through three space that are almost impossible to visualize, but the dot product fairly easily knocks down the angle between them. So the power here is starting to become apparent. Well, use that power. Go after this homework, muddle through all the stuff, pass along questions, and see how it goes. Pretty great examples here and pretty great homework coming up.